The light that you and I see with our eyes is just a small range of frequencies on a much larger spectrum called the electromagnetic spectrum. Different frequencies of light interact with matter in many different ways depending on the atomic structure of the material and its electromagnetic properties, also depending on the frequency of the light that's interacting with it. For instance, glass is clear to us because it permits light in the visible frequency range to pass straight through it, but move a little higher in the spectrum to ultraviolet and glass is no longer see-through. X-rays are another example of this. In the X-ray frequency, our bodies are clear, like glass, almost, while our bones are not clear because they have a different structure than our skin and organs. When light interacts with matter, a couple different things can happen. You can have reflection, where the light bounces off completely. You can have refraction, where the light enters the material and passes through it. Or you can have a combination of the two. You can also have absorption, where the light energy from a light particle, or photon, is absorbed and converted to another form of energy. This is what happens in the photoelectric effect, which is what Einstein published his first paper on. In the photoelectric effect, the energy from a photon is transferred to an electron in the form of kinetic energy. Basically, the photon comes in and smacks the electron, sending it flying off. These jumping electrons can then be harnessed to produce electricity. This is the underlying principle behind a photovoltaic cell, and this is how solar panels convert sunlight into electricity. We have millions of electromagnetic waves passing through our bodies at any given time. Most pass right through us with no interaction, but some of the higher energy waves can and do cause interference to our bodies, sometimes harmful. Now that I've given you the basics on electromagnetic waves and their interaction with matter, we are ready to talk about how to make things invisible. Scientists and researchers have made lots of important discoveries in the field of metamaterials. They have found ways to bend light so that it passes around an object as if it weren't even there. Now the hunt has been on to find a metamaterial that will do this for the visible frequency range, so that visible light will pass around an object, making it appear as if it weren't even there to an observer on the other side. A metamaterial is a material which gains its properties from its structure rather than directly from its composition, kind of like the way you can see through a screen on a screen door because of the holes in it. If you get up close to the screen, you can see that it's made of something, but from far away, it looks pretty clear. You can see straight through it. The main reason researchers have investigated metamaterials is the possibility to create a structure with a negative refractive index. Since this property is not found in any naturally occurring material, almost all materials encountered in optics, such as glass or water, have positive values for both permittivity, designated by epsilon, and permeability, the letter mu. However, many materials, such as silver and gold, have negative epsilon values at visible wavelengths. A material having either but not both epsilon or mu negative is opaque to electromagnetic radiation. This is due to the interaction of the surface plasmons. We'll go over that more later. In order for its structure to affect electromagnetic waves, a metamaterial must have structural features smaller than the wavelength of the electromagnetic radiation it interacts with. For instance, if a metamaterial is to behave as a homogeneous material accurately described by an effective refractive index, the feature sizes must be much smaller than the wavelength. Basically, the gaps between the atoms that make up this structure, this material, have to be smaller than the actual wavelengths of light that you expect to pass through it. So for visible light, which has wavelengths of less than 1 micrometer, typically 560 nanometers for sunlight, the structures are generally half or less than half the size, for example, less than 280 nanometers. For microwave radiation, the structures need only be on the order of 1 decimeter. Microwaves are much larger frequency waves. So microwave frequency materials are almost always artificial constructed as arrays of current-conducting elements, such as loops of wire, which have suitable inductive and capacitive characteristics. Metamaterials usually consist of periodic structures and thus have many similarities with photonic crystals and frequency-selective surfaces. However, these are usually considered to be distinct from metamaterials, as their features are of similar size to the wavelength at which they function, and thus cannot be approximated as homogeneous materials. Left-handed materials were first introduced theoretically by Victor Veselaggio in 1967. John Pendry was the first to theorize a practical way to make a left-handed material. Left-handed in this context means a material in which the right-hand rule is not obeyed, allowing an electromagnetic wave to convey energy or have a group velocity in the opposite direction to its phase velocity. Pendry's initial idea was that metallic wires aligned along propagation direction could provide a metamaterial with negative permittivity. Note, however, that natural materials, such as ferroelectrics, were already known to exist with negative permittivity. The challenge was to construct a material which also showed a negative permeability. In 1999, Pendry demonstrated that an open C-ring shape with axis along the propagation direction could provide a negative permeability. In the same paper, he showed that a periodic array of wires and rings could give rise to a negative refractive index. A related negative permeability particle, which was also proposed by Professor Pendry, is the Swiss roll. The analogy is as follows. Natural materials are made of atoms, which are dipoles. These dipoles modify the light vector by a factor of n, the refractive index. The ring and wire units play the role of atomic dipoles. The wire acts as a ferroelectric atom, while the ring acts as an inductor, L, and the open section as a capacitor, C. The ring as a whole therefore acts as an LC circuit. When the electromagnetic field passes through the ring, an induced current is created and the generating field is perpendicular to the magnetic field of light. The magnetic resonance results in a negative permeability. The index is negative as well. The lens is not truly flat, as the C and its nearby C's impose a slope for the electric induction. But basically, he found a way to make things invisible to microwave radiation. And now the hunt is on to find ways to make things invisible to the visible frequency of electromagnetic radiation. And I'm pretty sure that the aliens already know how to do this. That's why they are so good at avoiding us and our telescopes. For more information on metamaterials and meta-invisibility, I suggest you look up all these things, especially surface plasmons. They're very important to understanding these fundamental principles. I also suggest that you watch one of my other favorite videos. I'm going to have a link to it off of this one, which shows the these guys who go out and take pictures of UFOs, and they have one camera that sees visible frequencies and another that sees infrared frequencies, and they show where the infrared camera picks up an object that is not there in the visible frequency, and that's because that object is probably using meta-invisibility to avoid our detection. So, I hope you enjoyed it. Don't forget to rate 5 stars and subscribe to my channel.